the hidden force that turned Antarctica into a frozen continent. Scientists finally solved the mystery of why Antarctica froze first. Scientists may have solved one of the strangest mysteries in Earth's climate history: why Antarctica froze millions of years before the Arctic. The answer is not just colder air, falling carbon dioxide, or ocean currents. It may lie deep beneath the surface, in slow-moving forces inside the planet that lifted East Antarctica high enough for snow to survive. That matters because Antarctica did not freeze during a world like ours. It began building permanent ice around 34 million years ago, when Earth was still much warmer than today and the Arctic remained largely ice-free. The new explanation points to a sharper lesson. Ice sheets are not shaped by climate alone, but by the land beneath them. The puzzle of the uneven poles. For a general reader, the mystery is simple. Both poles are cold today, but they did not freeze at the same time. Antarctica developed a vast ice sheet around the Eocene-Oligocene transition, while large northern hemisphere ice sheets did not stabilize until much later. That difference has always been awkward for climate science. If global cooling alone explained polar ice, both ends of the planet should have moved toward permanent ice more evenly. Instead, the South locked into deep glaciation long before the North. The reason now appears to be geography, geology, and timing. Antarctica is a continent sitting near the South Pole. The Arctic, by contrast, is an ocean surrounded by land. That one difference changed everything. Ice can grow more easily on high land than over open ocean. On a mountain or plateau, temperatures are lower, snow lasts longer, and each surviving winter layer can become the base for the next. Over the Arctic Ocean, there was no equivalent high-altitude platform at the pole where permanent ice could gain the same early foothold. The deep Earth force beneath Antarctica. The new study points to a process known as mantle waves. These are slow disturbances deep inside Earth that can move beneath continents after tectonic plates break apart. In this case, the process began when Antarctica and Africa started separating during the Jurassic period, more than 140 million years before Antarctica's Great Freeze. Over huge spans of time, those deep Earth processes helped lift parts of East Antarctica. The land did not jump upward overnight. It rose slowly, building an elevated plateau and helping shape the Gamburtsev Mountains, a buried mountain range now hidden beneath the East Antarctic ice sheet. This is the critical point. Antarctica did not need the whole planet to become freezing cold first. It needed parts of its surface to become high enough for snow to survive through summer. Once that happened, small glaciers could form, expand, and eventually merge. The threshold appears to have been around 1.5 to 2 kilometers of elevation. Below that, snow was more likely to melt away each year. Above it, year-round snow could accumulate, thicken, and begin the long transformation into an ice sheet. Why height changed everything? The easiest way to understand the finding is to think about climbing a mountain. Even in a relatively warm climate, the air gets colder as elevation increases. A landscape that is too low for permanent snow can become ice-friendly if it is lifted high enough. That appears to be what happened in East Antarctica. Computer models reconstructed how the land surface changed over roughly 100 million years. The simulations suggest that by about 45 million years ago, much of East Antarctica had already risen above the elevation needed for mountain glaciers to begin forming. By around 34 million years ago, the system crossed a tipping point. Falling carbon dioxide helped cool the planet, but the raised Antarctic landscape gave ice somewhere to survive. The land was ready when the climate window opened. This also explains why Antarctica's ice did not appear everywhere at once. Separate research on ancient sediments indicates that Antarctica began freezing from East Antarctica, while West Antarctica remained much greener for millions of years longer. West Antarctica appears to have followed later, once conditions became colder and ice could spread farther. Why the Arctic had to wait? The Arctic's delay now makes more sense. There is no continent at the North Pole. The pole sits in the Arctic Ocean, which meant there was no central mountain chain or high plateau capable of catching snow and protecting it through warmer periods. That does not mean the Arctic never had glaciers nearby. Glaciers came and went across northern landmasses over tens of millions of years. But a stable polar ice system required colder global conditions, lower carbon dioxide, and later northern hemisphere ice sheet growth. Antarctica had a geological advantage. It had land in the right place, and that land was lifted to the right height. The Arctic needed the climate to fall much further before ice could become permanent at lower elevations and across ocean-centered polar conditions. This makes the story more interesting than a simple tale of cooling. Earth did not just turn down the thermostat. It rearranged continents, lifted mountains, changed atmospheric chemistry, and allowed ice to exploit the shape of the land. What this reveals about Earth's climate system. The discovery matters because it shows how long-term geology can decide climate outcomes millions of years later. A process that began with continental breakup in the Jurassic period helped prepare Antarctica for glaciation long before the ice actually arrived. That is a powerful idea. The planet's surface is not a passive stage on which climate performs. Mountains, plateaus, ocean gateways, and continental positions can decide where climate change becomes locked in. It also gives scientists a clearer way to study ancient transitions. The Eocene-Oligocene shift was one of the major climate turning points in Earth history, when the planet moved from a warmer greenhouse world toward the icehouse conditions that still shape today's climate system. The research suggests that falling carbon dioxide was essential, but not sufficient on its own. East Antarctica's uplift made the cooling more effective by giving snow and ice a stable base. Once ice spread, it also reflected more sunlight back into space, reinforcing cooling through the ice albedo effect. Why it matters now. This is not just a story about ancient Antarctica. It changes how scientists think about the future of ice sheets. If the shape of the land helped decide where ice first formed, then the shape of the land also affects where ice may hold, retreat, or collapse. East Antarctica is often treated as the more stable giant, while West Antarctica is seen as more vulnerable to ocean-driven melting. The history supports that broad distinction. East Antarctica's high terrain helped ice take hold early, while West Antarctica's later glaciation points to a more fragile relationship with climate and ocean conditions. That does not make East Antarctica safe in a warming world. It means its response is different. Ice sheets are not uniform slabs. They are systems shaped by bedrock, elevation, snowfall, ocean heat, atmospheric circulation, and feedback loops. For future sea level projections, that matters. The East Antarctic ice sheet holds an enormous volume of frozen water. Even small improvements in understanding why it formed and how it stayed stable can sharpen models of how it might behave under sustained warming. What happens next? The next step is to test the model against more geological evidence. Scientists will want better maps of the buried Antarctic landscape, more sediment records, and stronger links between ancient topography, carbon dioxide levels, and ice sheet behavior. The biggest unresolved question is not whether Antarctica froze before the Arctic. That part is clear. The deeper question is how close today's ice sheets are to thresholds of their own. The new study points to a hard lesson from deep time. Ice sheets can appear when climate, land, and feedbacks line up. They can also weaken when those supports are disturbed. Antarctica froze first because Earth quietly built the right stage beneath it, long before the climate delivered the final push.